This is the Science Podcast for April 2nd, 2026. I'm Kevin McLean. First up on the show, a new path to calculating the Hubble constant. This value for how fast the universe is expanding is typically determined in one of two ways, one favored by cosmologists, the other by astronomers. But the resulting values from these methods are consistently different. Staff writer Daniel Clery joined Sarah Crespi to discuss how a phenomenon called gravitational lensing could help resolve the dispute over the speed of the expanding universe. After that, freelance producer Ella Feder talks with neuroscientist Mauro Costamaggioli about tuning the integrated stress response in the brains of mice. They discuss how this pathway affects protein synthesis in cells under stress, how controlling this activity can both hamper and restore brain function in mice, and why the integrated stress response may be a good therapeutic target for many cognitive dysfunctions ranging from Alzheimer's to Down syndrome.
We know the universe is expanding, but there is a long-standing debate on exactly how fast it's happening. The debate is to differing results from two methods that are used to calculate this speed, also known as the Hubble constant. This week in Science, staff news writer Daniel Clery wrote about researchers attempting a third way of doing this calculation that may resolve this Hubble tension. Hi, Dan. Welcome back.
Hi. Nice to be here.
So let's go through how to calculate the Hubble constant. It seems like you have astronomy style and cosmology style. Like those are the two.
Yeah, that's essentially it. The Hubble constant tells us how fast things are flying away from us. So we know the universe is expanding, and the further away you look at something, the faster it's flying away from us. This was first done by looking at galaxies with telescopes, trying to estimate how far away they were. I think it was originally just done by size. Then you get the speed they're going away because their light is redshifted. So the Doppler effect moves all of their light slightly towards the red end of the spectrum, and that tells you how fast. So that's really easy, telling how fast something is moving away. The difficult bit is measuring the distance to that object. What scientists have traditionally done is use things called standard candles. So if you have an object where you know how bright it is, you look at how it looks at a distance where it'll be much less bright because it's so far away, and you compare the two, and that gives you a measure of the distance. There are stars called Cepheid variables, which pulse at a certain rate, and that tells you how bright they are. So if you can see a Cepheid variable in a distant galaxy, you can see how bright it appears, you know how bright it really is, and then you can tell how far it is away. And they do similar things with supernova. There's a particular type of supernova called a type 1a supernova, which again, you can predict how bright it's going to be at its peak brightness, and that you can see even further away because supernovae are very bright. And so people have measured the distance to galaxies 1 billion light years away using that method. With that method, they've come up with a value for the Hubble constant, which is 73 kilometers per second per megaparsec, I think is the actual thing.
So 73 is the standard candle version, which is astronomers. That's what astronomers, they're observing things, they're making calculations based on their observation. They say 73.
Yeah. Then in recent decades, cosmologists have come along and they've said, actually, we could measure the Hubble constant a different way. So they look back in time by looking very far away to this glow that covers the whole sky called the cosmic microwave background. And that's a sort of echo of the universe as it was 400,000 years after the Big Bang. There were no stars, there were no anything apart from just particles and photons banging around. And then all of a sudden, some of the particles collected together to become atoms. Everything became transparent, and this radiation just sort of wafted out into space. And you can see that now. It's microwave radiation, but there are slight variations in its temperature across the sky. And these ripples can tell you all sorts of things. And one of the things they can tell you is what the Hubble constant was then. Cosmologists can calculate the local value of the Hubble constant, and then they figure out what it would be now,
Like fast forward in time.
to the present day, using cosmological theory. So their method rests on theory, but they're fairly confident about that theory. And they come up with a value that's about 67 kilometers per second per megaparsec.
Okay, so 67 is the cosmology value that's looking at the cosmic background radiation. And the astronomy is 73. So we're a little bit of a different. And then, of course, we got to talk about error bars in physics because people really care about error.
That's it. When those measurements were first made, they had wide error bars that overlapped, and people thought, okay, there's just some bias, they'll
get it together.
Gradually merge together. And so people have redone the calculations, gathered more data. Error bars have got smaller and smaller and smaller, but the two figures haven't moved closer together. So the two methods come up very strongly with differing values. The problems here could be that the cosmological theory is wrong and needs to be adjusted, or it could be there's some systematic error in the way people measure the distance to standard candles that is biasing that result and making it higher than it should be.
They both have complaints about each other's approaches.
Exactly.
They don't agree. Error bars are getting smaller, but they're not actually causing these values to overlap. We're going to come up with a third way. We're going to have another way to do this calculation based on independent observations that are not either what's going on with the microwave background and what's going on with the standard candles. What is the third way?
So this involves a phenomenon called gravitational lensing. So when you've got something extremely massive sitting somewhere in the universe, like a galaxy or even a cluster of galaxies. So galaxy clusters can have hundreds or thousands of galaxies in them. And so they're the largest structures known in the universe, so the most massive structures that are held together with gravity.
They're centered on massive black holes, and then they have all their stars, and then there's more. It's amazingly big. It's kind of hard to conceive.
Yeah, exactly. They're just huge. You can't really get it in your head. But anyway, these massive things, what they do is they bend the path of light. Gravity will actually bend space, and then light follows space. And so the light gets disturbed from a straight path, and it can act as a lens. So if you have a galaxy sitting there in front of a more distant object, if viewed from Earth, what you can see is multiple versions of that more distant object that the light has been bent in different ways by the lens in the middle, and so that you see different versions of the distant object. Or if it's like an extended object, like a galaxy that's getting lensed, it can produce distorted versions of it, like a funhouse mirror. So people use that to look at very distant objects as if you're using a giant telephoto lens. But it has another interesting effect in that the light that follows different paths and produces different images, has different transit times. So if, say, in your very distant galaxy, a supernova goes off, and you're watching it, and you're seeing the light go around a gravitational lens, the supernova might appear in one place, and then appear in a different place, and then in a third place, all lensed by the intervening galaxy or galaxy cluster.
Why would there be different appearances? Why would it show up at different times or places?
The different places are because the light has followed a different path. A gravitational lens is not a regular thing like a glass.
It's not a tube where we pass the light through to focus it into like one.
It's just a wacky mirror. Some funhouse mirrors, if you look at them, it divides your body into a top half and a bottom half. It's the same with the light coming from this distant object. Some of it follows one path through the wobbly lens, and some of the light follows a different path through the wobbly lens, and those paths are different lengths. So if it's an event which is fixed in time, like a supernova, one image of it is going to get to you faster if it's going a shorter route than another one that is going a longer route. And you add the complication that very extreme gravity, like around a galaxy cluster, slows down light because it slows down time. This is one of the effects of general relativity, the theory of gravity, is that time is slowed down. So the effect is that light travels more slowly. So you end up seeing this supernova happening at different places and at different times, which is a really cool thing. It's quite clever. So what you can do then is if you have a supernova that does that, where it appears at different times, different places, you can use that to sort of triangulate back to where the supernova came from and calculate its distance. So the different time delays between the different images give you a handle on the distance to that distant object, combined with their distribution on the sky, how far apart they are on the sky in the images, and also the gravity of the lens. So all of those things together allow you to calculate how far away that supernova is, and you can calculate how far it's flying away from its redshift, and then you can do the calculation.
This method that you described, using gravitational lensing of a very, very giant thing to look at something far away that shows up at different times and places and gives you this ability, it's been done. People have tried this. They have tried to calculate the Hubble constant out of it. And what kind of values are they getting?
At the moment, very varying values. They're doing one of these at a time, and there's a lot of uncertainty still. So, I think some values are less than 67, so even lower than the cosmologists. Others are closer to what the astronomers have come up with standard candles. So the error bars are still large, and the accuracy is obviously a bit off because, they're getting very widely spaced values, but they're getting better at it all the time.
What are the timescales? Like, how long do you have to wait between different versions?
It depends on how strong the lens is and how big a diversion the light goes through. So if you're using just a single galaxy as a lens, which isn't a very powerful lens, the time delays tend to be much shorter. They might just be days or weeks. But if you're using a very massive galaxy cluster and the light goes a very roundabout route to get to you, it can be years or decades later. They found one supernova, they've seen the supernova go off in one image, and they calculate there's another image coming that's going to be in 60 years' time.
Oh, wow. That's so long. I don't have the patience.
No, exactly. That's probably the poor astronomers who discovered it won't see it in their lifetime, probably.
So this does remove some of the kind of assumptions or what may like with standard candles or with the other calculation method using the cosmological theories. But it does introduce other kinds of complexities. And one of them is weighing up a galaxy. So being able to decide how much of a deflection this takes and how long it will take is part of that puzzle as well. So how are they doing that? How are they deciding how big a cluster of galaxies is?
It's a complicated thing, but people have been doing it for a few decades to sort of study them and understand how the lenses work so they can use them as a magnifying glass. What you do, first of all, is you figure out, in your image, when you're looking at it, you're looking a long way through space. So you don't know initially which galaxies you're seeing are part of the cluster and which ones might be in the foreground or the background. So you have to take a redshift of all the objects, and ones that all have a similar redshift are all at the same sort of distance. So you can build up, a membership list of your galaxy cluster, and then you can do other things such as look at the brightness of individual galaxies, and that gives you a sort of idea of how many stars there are in it. Then you have to guess how much dark matter is. So dark matter is this stuff that holds galaxies together. And again, people have sort of ways of estimating how much dark matter there is associated with galaxies. And finally, you can also look at galaxies with these sort of special spectrographs that essentially divide up an image into squares and give you a spectrum that's breaking up the light into its different wavelengths for each square of an image. And you can see how much each square is redshifted or blue shifted, showing the movement of all of the material in that square. Getting information about the movement, that tells you how big the mass of the galaxy is, because massive galaxies make the stars around them move faster because the gravity is stronger.
There's actually a lot of experience doing this, like in the community. And it's really just a matter of kind of putting that together with these observations of differently timed images coming over And that is kind of where we are now. We're waiting for those images that are coming in sequence, being magnified by these lenses. And luckily, we have a ton of instruments coming online or just online that are going to kind of supply a lot more fodder for this calculation.
I mean, there's only about 3 or 4 supernovae that have been found that people have been able to do this with so far, that have produced multiple images with time delays that you can measure. To get a better fix on the Hubble constant, you just need more of them. And things like the Vera Rubin Observatory, which is a survey telescope in Chile, that's about to come online and should find lots of these things because it sort of scans the sky every few days, the whole sky it can see from Chile. So it'll spot things that suddenly appear or get brighter, as a supernova would do. And so it would be a great thing for just finding lots of supernovae. And so among all the supernovae that it finds will be some that are lensed. And those are the ones you're looking for. So they're hoping, to get many, many more of these things. And so they can get a better overall measurement of what the Hubble constant is by this method. And if they can do that and improve the precision of it, then it starts to become important.
This was my question. Why?
Yeah.
Why do we want to know this?
You want to do it because you want to see which way it's going to go. Is it going to side with the cosmologists who are looking at the cosmic microwave background, or is it going to side with the astronomers that are using standard candles? If it very obviously favors one or the other, that will suggest where the problem lies.
There's something wrong with the other guys.
Yeah, exactly. So where the problem that creates this Hubble tension lies, and then you could start looking for that problem and figure out which is right.
Is there anything else that we can do with this more precise and believable value of the Hubble constant? Is there any other kind of problems that it'll address?
Yeah, there are. People are thinking when they can improve it even more, it should help them to understand this issue of dark energy. So dark energy is a sort of mysterious force which seems to be accelerating the expansion of the universe. So the universe is always growing, as we know, since the Big Bang. And for a long time, astronomers thought it would be slowing down because gravity would be constantly pulling inwards. But in fact, when they measured, they found that it was speeding up. And so they had to come up with some explanation. They tweaked the theory of gravity to add an extra element to it to explain this accelerating expansion, which they call the cosmological constant. But usually scientists refer to it as dark energy. There's some sort of energy that's pushing things out faster and faster. That's another thing that they might be able to shed some light on using this gravitational lensing technique.
All right, Dan, this has been super fascinating. Thanks for talking with me.
Yeah, thank you.
Daniel Clery is a staff writer for Science. You can find his story and some beautiful graphics at science.org/podcast.
Also out this week in news, staff writer Jenny Smith wrote about p-tau blood tests for Alzheimer's disease, which can predict within a 3 or 4 year window when someone is likely to develop dementia. The test is currently only approved for patients with cognitive symptoms, but doctors say it's already being used to test asymptomatic people. Also, on the cover of Science, research on the specialized arm of male octopuses called a hectocaudalus. Males use this arm to identify females and navigate their internal organs to reach the oviduct and deliver sperm, and it turns out cells on this arm can also sense progesterone, aiding in the reproductive process. In Science Advances, new research on how the eye chooses which wavelengths to see best. Evidence suggests that human vision uses opposing red-green and blue-yellow color signals to bring the world into focus. Stay tuned for Ella Fetter's conversation about how harnessing the integrated stress response could help treat problems with memory and cognition.
Submissions for the Eppendorf and Science Prize for Neurobiology are now open. The prize for neurobiology recognizes outstanding young researchers, age 35 and under, for exceptional neurobiological research conducted in the past 3 years. The winner receives $25,000 and publication of their essay in Science. Apply now at science.org/prizes before the June 15, 2026 deadline. Apply today for a chance to win the Science and Sci-Life Lab Prize for Young Scientists. This annual prize recognizes outstanding doctoral research in life science, including cell and molecular biology, genomics, proteomics, systems biology, ecology and environment, and molecular medicine. Apply today at science.org/prizes for a chance at the $30,000 grand prize. Submissions close July 15th, 2026.
When one of our cells is in trouble, maybe it's not getting enough oxygen or it's been invaded by a virus, one of the most powerful tools it has for coping is what's called the Integrated Stress Response, the ISR. It's basically a way for a cell to hit pause and regroup. So picture a cell as a factory. Maybe things are starting to bunch up on one of the conveyor belts. You hit that red emergency button, and all the machinery stops, and the workers can fix whatever's gone wrong before they restart the machines again. The integrated stress response basically does this for cells. It dials down most protein synthesis, but boosts some key proteins needed for recovery. You can see why that would be helpful. But what happens when the ISR won't turn off? When your cells are perpetually in emergency repair mode? There's a lot you can't do without new proteins. A new study led by researchers at Altos Labs investigated the role of all this in cognitive function. Mauro Costa Mattioli is a principal investigator at Altos Labs. Dr. Costa Mattioli, welcome to the show. To start with, you describe creating these mice where the integrated stress response appears to be in overdrive, it won't shut off. How did you create these mice?
So, from the evolutionary perspective, if this were to be a pathway that regulates memory, we thought that there might be patients or individuals that they have cognitive decline or intellectual disability, and they have mutations in the pathway that activate the pathway. So we identified patients that have specific mutations in particular genes, and we replicate that mutation in mice, such we have a humanized model of the disease, and we discovered that when we do this, the pathway is activated. These animals, they have cognitive problems. The connections between brain cells became actually not very effective. But if we were to inhibit the ISR, we are able to pretty much reverse all those deficiencies which are associated with this mutation.
Okay, I want to slow down a bit. We'll get to the alleviation in a moment. But to recap, you were thinking a hyperactive integrated stress response is associated with cognitive problems. So you actually worked with a gene that's called PPP1R15B. I won't say that too many times. In humans, there is a genetic variant that's associated with both hyperactive ISR and with cognitive impairment. You take that genetic variant, put it in mice, and you see the same thing. So what are exactly these cognitive problems you see in these mice?
So basically what we did is we tested the ability of the animals to form a memory. And what we do in those animals is say we expose them to a particular environment several times. And we couple that environment with an aversive experience. We give them a small food shock. So as a result, those animals will associate that environment, let's say Toronto, the weather of Toronto, with a bad experience, right? So every single time that you think about Toronto, you would think about a bad experience, right?
Thanks a lot. Thanks a lot. Okay.
I shouldn't say that about Toronto. I'm about to go to Toronto.
You know what? On behalf of Toronto, I forgive you. Please carry on.
So now the animals, as a result, the animals will freeze. Every single time that you expose them to that environment, will freeze because they will believe that the food shock is coming, but it doesn't come. And if you were to be a normal animal, that response became sustained. In a similar fashion, if I tell you something 4, 5 times, 6 times, it's very likely that you will remember it for quite a bit of long time. But those animals, the connections between those brain cells became actually impaired or deficient or weakened. Those animals, essentially, they freeze much less. A clear indication that the long-term memory is actually deficient.
So they're having this negative experience, but they're having trouble remembering it for the future.
They have to be precise. It might not be, it's not that they have the ability to form the memory and then they have no access to it. They cannot form it. They cannot form the memory, those animals. I'm pretty much recapitulating what happened in the patients, because the patients, they have intellectual disability. Those are people which have been born with these mutations, And now those individuals, they also develop intellectual disability. And now we know the reason why.
And then the mice, were their brains smaller in this?
Like the patients, because when the ISR is activated, the ability of synthesized proteins is actually reduced. It's not that you completely abrogate the ability to produce proteins. You attenuate it, you reduce it. So our interpretation is one of the manifestations of this, specifically in the brain, is that the brain actually are smaller in the animals. And in the patients have microcephaly. So they also have a small brain. So we are not only recapitulating the cognitive decline, but we are also recapitulating that feature of the animal, that structural feature that essentially sometimes define patients that, they have cognitive dysfunction.
Okay, so you have these mice, and then you approach it from the other direction. So this time, instead of taking that gene variant from humans, you take a protein from a virus, the African swine fever virus, and this produces the opposite effect of that human gene. Instead of making a hyperactive integrated stress response, it puts the brakes on the integrated stress response.
It's truly an evolution story. A colleague of mine, Tom Deaver from NIH, has published a study in which he has found that in this virus, you have this very small protein, the smallest one. The normal protein in mammalian cells is over 700 amino acids. This is about 60, super tiny amount. So then we took that viral protein, which is similar to the human protein that is mutated, and we discovered that there is adaptations in this molecule that make it incredibly effective.
Effective at suppressing the integrated stress response.
Suppressing the integrated stress response, right?
And this is really important for a virus, right? If a virus enters a cell and the cell shuts down all protein production, well, it's not going to make any viruses. That's not going to be... So they need a way to turn the machinery back on.
The viruses, they have this incredible strategy to cope with this because the virus use the cellular machinery. It use our ribosomes to produce their proteins, right? So then the virus says, you want to screw me up because you want to stop the ability to synthesize proteins, so then virus doesn't come up. Guess what? I have a strategy to cope with this. So based on this, and based on the fact that to develop gene therapy, typically the gene therapy is delivered using another virus, which is called AAV, but you have a limit capacity of how much you can put inside. We found, oh my God, this is such a small molecule, and it's so potent that perhaps we can use it to essentially suppress the ISR almost in a disease agnostic fashion. It doesn't matter what is the cause that turn on the ISR. Thanks to this viral protein, thanks to, hundreds of, perhaps millions of years of evolution, we have found a way that now you can reawaken the ability, you can turn the switch on in all those conditions.
So you found a way to switch off the ISR and reawaken protein synthesis in these cells. You tried this in a few different kinds of mice, in older mice that are models of Down syndrome, and mice that are Alzheimer's models. You give them this protein derived from the virus.
Yes, into the brain.
Into the brain.
One single injection.
One single injection.
One single injection.
And how do these mice change? What did you see?
When we test this memory task, if they are not treated, they perform very poorly. But now, if we treat them with this intervention, they perform very similar to normal mice. They perform much better. When we measure the strength of synaptic connections, those connections, the strength is very weak, is very deficient. But when we do that intervention, it becomes very stable, like a long-term memory.
So they're remembering that foot shock that they got, and
their memory becomes practically normal in those animals, right? So you are essentially rescuing, or you are reversing the cognitive decline, which is associated with all those conditions. And if you think about memory, I think perhaps the unconventional approach or concept that we are putting forward here is if you have a deletion in chromosome 2, you can have intellectual disability. If you have an extra chromosome 21, you have Down syndrome and you have intellectual disability. The genes that you have in chromosome 2 are very different than the genes that you have in chromosome 21. but there is something in common. And what is common is that you have a change in the homeostasis of the cell. And when you have that change, the ISR gets activated. You have a problem in the factory. So now you need to essentially shut down the ability to synthesize new proteins. And as a result of this, you cannot form a long-term memory unless now you inhibit the ISR. So, for many years, we have essentially have silos of diseases, Alzheimer's disease, Down syndrome, like completely different diseases. Maybe there's a common denominator, at least for the cognitive decline, that one can tackle. It's sort of is a strategy a bit different than the precision medicine that everyone is using. Now we identify what something is common in all disorders. And there's molecules that are being developed, in the clinic, ISR inhibitors, there's those gene therapy approaches. So, time will tell how impactful this can be in cognitive disorders, but we are incredibly excited about the possibility of having any impact in society.
Thank you very much for joining us.
Oh, it has been a pleasure to be here. And yeah, fantastic.
Mauro Costa Mattioli is a principal investigator at the Altos Labs Bay Area Institute of Science. Altos Labs was started in 2022, and its official mission is cellular rejuvenation, undoing the damage caused by disease and injury. You can find a link to the paper we discussed at science.org/podcast.
And that concludes this edition of the Science Podcast. If you have any comments or suggestions, write us at sciencepodcast@AAAS.org. To find us on podcast apps, search for Science Magazine or listen on our website, science.org/podcast. This show is edited by me, Kevin McLean, Sarah Crespi, and Ella Feder. We had production help from Podigy. Our music is by Jeffrey Cook and Wen Koi Win. On behalf of Science and its publisher, AAAS, thanks for joining us.
Meet the new iSIMS, the single talent acquisition platform that's fully future-ready. It works wherever and however you hire, with insights no one else offers. One solution that fits seamlessly into your existing tech stack, which is why IT and HR leaders trust it. With the best of enterprise-grade software and AI, iSIMS helps you identify and secure the right talent faster. iSIMS, powering exceptional hiring. Learn more at isims.com.